All right, we're up and running. We have a huge audience here. Tom, Zimmie, we're doing soils and groundwater. I have a bunch of handouts, and I have some extras, so I'll leave them in the civil office. If somebody wants to pick them up later, they can. And it includes, well, let's see. What I wanted to say was that you better look at the NCES book, because when you look at the book, that's what you will get before the exam. As far as I know, the stuff I have here, it said is good until June or something. So that's the stuff here. So that's now the page you're looking at here is from an old book, but the real stuff is, the latest stuff is here. It doesn't matter. But what I want to point out was, when you look through this stuff, there's more or less, you can gauge what they're going to ask you, because they can't ask you too much complex things. Everything that they're going to ask you is pretty much in here and defined. That's whether it's Darcy's law or how to use the flow net or whatever, and that's the key thing. So what I did from that NCES book, you may want to make note here. The geotech part is on page 152 to 157. Now, not all of that is being applicable to the environmental, but some of it is. If you're taking the civil exam, well, of course, you probably want to look through all the 152 to 157. However, you say, well, the groundwater stuff should be in the environmental. It's not. It's not in the environmental. It's in the civil part, and it's on page 171. It's only one page, and we can look at that later. And if you read the NCES book, they tell you, and they give you a listing of everything that's there. And so if you're taking the environmental exam, you're probably, in the soils part, you have to go to the civil part. And if you're, I suspect in part of the environmental exam, you probably have to go to the chemical part. But anyway, you want to look through it because that gives you a pretty good idea of what is there, and you want to look at it so you know you'll have it. You don't have to memorize much. And that's the idea. So what I thought I was going to do today, I'll show you you have these handouts. We can worry about that later. I thought the first thing we do is do some problems. We're going to do problems first, and then we can go, if we have time left over, we can kind of go through some of the other handouts I'll show you. Because we do have a chapter from a review book is here too, etc., which I think you can get in the civil office, as far as I know. But anyway, so let's start with some problems. In groundwater, primarily. And I think they said they could be from like 9 to 14 problems in the groundwater area. That would be in the environmental part. But there's also stuff in the civil part that has to do with groundwater, but it's mostly a different aspect. But anyway, this is from an old exam, an old book, and I don't know where it even came from, but it's applicable problems. So it starts here, the storage coefficient, S, of a confined aquifer. And I assume you know what a confined aquifer is. And he gives you this. And then he says, and he defines all the terms in the equation. And then he says a different expression for the storage coefficient is this. And again, everything is defined. And what they want to know is, what's the barometric efficiency? Well, if you look up here, you see, gee, what's barometric efficiency? That's the big letter B. So the big letter B is the barometric efficiency. It's not down in here. And so I think it should be obvious that what you're going to have to do is combine the two equations. I should point out that if you get a really long problem, if you look at this and you don't have any idea what you're doing, and you think you're going to spend 15 minutes on this problem, forget it. You can't do it. You don't have the time. So in some cases, take a guess and move on. And maybe make a note. Oh, I got to go back to problem such and such if I have time. Because you probably won't have time. So anyway, and there are some lengthy problems that I advise the students, don't even mess with it. Take your guess and go home, move on. But this one isn't too bad. In other words, I think you would look at this one and you say, oh, I'm going to equate the two things together. It shouldn't be too bad. So here's the solution. And so it says set the two equations equal. And a lot of things go out. you don't need gamma W, and they don't give you gamma W, the weight of water, because it's going to go out. And so anyway, a whole bunch of things cross out. You can look at it, and the only thing you're left with is this B. I'm solving for B, and I only have 3 terms here. And they're all given to you. I mean, defined. They said the porosity was 0.2, and they gave you all these numbers here. So the only difficult thing is playing with these numbers. So as long as you can handle all these exponential problems, boom, and you get the 0.0051. That's all. So that one's not too bad, if you recognize how to do it. If you don't recognize how to do it, you can cut it off a lot of time. Okay, then there's this is another problem. It says a retardation factor. Retardation factor, there is something in the environmental part about retardation factors, because that has to do with groundwater contamination. And what the retardation factor means, how fast is a contaminant going to go relative to the groundwater? And if the retardation factor is 1, then that means there's no retardation. In other words, the groundwater is moving as fast as the contaminant is moving as fast as the groundwater. On the other hand, if you have a number higher than 1, I think this one is going to be 5. Yeah, 5. That's going to say, that means it's going to go, the contaminant is going to go 5 times slower than the groundwater. Because there's a lot of things can happen. Depends on the contaminant. It might precipitate, might cation exchange. There's a whole funny bunch of stuff. Only if you have something like simple salts, sodium chloride or something like that, it dissolves so much in water it'll move. That's what they call a conservative contaminant, and it'll move at the same speed. But in this case here, you don't have to know all that. It's just saying the retardation factor is 5, and therefore what's the answer? And you look at it, it says, well, 4/5 of the contaminant is absorbed into the solids. Well, I don't know that. That doesn't tell me anything about that. 4/5 of the contaminant is dissolved in the groundwater. I don't know that either. And so the groundwater travels at 5 times the speed at which the contaminant travels. That's the answer, okay? And then it says D, the contaminant. Okay, that's no good. Now, interestingly enough, they screwed up here. It's a typo. They said the answer is A, and then the answer is C. Okay, so that's the actual answer. And there it is. And this is in the environmental part. So it's just the retardation is by a factor of 5. And in fact, they even said it. That's what he said. Therefore, the groundwater velocity is 5 times the contaminant velocity. Well, of course, the answer is C. It's just a typo. So the answer is C. That's on the handout. No equations. Here again, no equations. Basic stuff. The water level of a well drilled into Artesian Aquifer is what? And look at it. Is it the same level? This is an Artesian Aquifer now. So we're talking about an Artesian Aquifer. I guess I better do it here. So if we have groundwater here, we have an Artesian Aquifer. So this is the aquifer that has the water. It's a confined aquifer. And if you put in a well, that means the water is probably going to be higher than the aquifer. And this part is like sealing it off. It's like a pipe. That's what a confined aquifer is. If you've taken groundwater, you know that. That's different than an unconfined aquifer, which is just a water table aquifer. So therefore, looking at this picture, you'd say to yourself, the water level is the same at the top of the water in the aquifer. That means the water level would be here. Well, that's not right. Then it wouldn't be an Artesian aquifer, a confined aquifer. It's above the level of the top of the water in the aquifer. Well, that looks about right, huh? And then C, below the level? Well, they can be below. That's stupid. And then it's either at the same level as or above the level of the top. That could be confusing. That's one of those, if you overthink it, you say, oh, gee, it could be the same level. No. So the best answer is obviously B, okay? And he explains it. Artesian aquifer, water pressure, okay. All right, next problem, 52. A flow pattern is a 3-dimensional representation of total head. When water is pumped out of an unconfined aquifer, the flow pattern of the groundwater has what? No appreciable change due to removal? Well, that's not right. I mean, obviously I'm pumping water, something's going to happen, right? A linear slope? I don't know that. It's not going to be linear. A cone of depression? Or a semi-spherical? And the answer is C. It's a cone of depression. We're talking about an unconfined aquifer now here, so I got the surface, and here's my water table, and I'm putting in a well, and I'm pumping the water out, and as I pump, I depress the water table here. That's different than a confined aquifer. You're not depressing the water here, because the water is like in a pipe. You could depress the head, but you can't depress the water in here. So here you do, though. This is water. So you're doing this, and this is it's radial flow. It's a cone of depression. It looks like a cone. It's an inverted cone. So again, it's C. The answer is C.
And the top one, number 50, the confined aquifer, that's because there's a barrier at the top of the aquifer preventing it from going.
Yes, this could be bedrock. You would normally have something, the aquaclude. They call it an aquaclude, because otherwise, if this was, for instance, if right above this was sand, then it wouldn't be confined. Okay. And a confined aquifer can even just be in bedrock. It's still, there's got to be we don't have time to get into that. But if this part here, you have to worry about it. It could be leaky. I mean, is Mother Nature going to be perfect? You're going to have this thing go for miles, and there's not going to be any water leaking up into the dock. Come on. But that's, at least in concept, yes. You do have to have something to seal it. Okay. All right. 57. A confined aquifer at sea level has a hydraulic head of 2 meters. The absolute pressure at the top of the water in the aquifer is most nearly what? What they're asking is, I got this confined aquifer. So here's my confined aquifer again. And it says it has a hydraulic head of 2 meters. So above here, in other words, I got a well in here, and I got this water coming up to here, and this is 2 meters. So it's definitely Artesian, okay? And the question is, what is the absolute pressure? Now, normally we don't play with absolute pressure, but it's asking for absolute pressure. That's the key here. And absolute means you got to add it up on top of the atmosphere, right? Like 14.7 is the atmosphere, right? So therefore, if I had a 2 psi pressure, I'd say, gee, the absolute is 16.7, right? Except here now it's going to be in atmospheres. And so you got to, in other words, you got to convert atmospheres. And so he says, okay, I got rho GH, and I know that rho, I got 1,000 kilograms. You got to worry about units here. That's the only complicated thing. So I got 1,000 kilogram per meter cubed. 9.8 is G. The H is the 2. And then how much do I have? How much atmosphere per pascals? And again, that's the 9.8, but it's 10 to the minus 6. So you could look that up. And so you get 0.19 atmospheres. So it's 0.19 atmospheres plus 1. 1 atmosphere is a natural, okay? And that's 1.2 atmospheres. You could do that. How did I do it? How would I do it? Or maybe, I don't know. Maybe I said to myself, what's an atmosphere? An atmosphere is about 30 feet. And what's 2 meters? That's about 6 feet. So I got 6 over 30. That's about 0.2. That's about 0.2 of an atmosphere. So therefore I said, yeah. So the answer's got to be 1.2. And of course it's not. It's 1.19. Good enough for government work though, right? Yeah. And I just did that in my head right off the bat. So if you can convert back and forth like that, it's okay. If I had to do it this way, it'd take me 5 minutes. I just did it, said, oh yeah, 6 over 30 feet. Okay, whatever. Okay. I don't remember what yearbook this came from. So let's do some more. Now these problems here were from the book that was in the civil office, the review book, practice exam. That's these. And I just grabbed the ones from the groundwater part, which they said was from 91 on. Okay. So, and again, if you get the book, you know yourself. You can look at it. But anyway, okay, constant head permeameter, soil specimen diameter of 4 centimeters, hydraulic gradient of 4, the constant is 25 centimeters per day. What's the hydraulic conductivity? Well, this is a soil mechanics problem just as well as an environmental problem. But if you're going to do groundwater, you got to know this. Okay, so it could be a civil problem just as well as a environmental problem on the test. So anyway, okay, Where are the answers? Okay. So this is just a Darcy's law, Q equals KIA. Anything. But rather than be fiddling around with it, let's go to the answers. Groundwater and soils, by the way, this is in the book, and it says 9 to 14 typical problems. And it's kind of defining the kind of stuff that you have to worry about. But anyway, here's the solution to this one here about the problem here. So I have it's Darcy's law, Q equals KIA. I got 25 cubic centimeters per day that was given in terms of Q. The V is 4. He says hydraulic gradient. No, V. Hydraulic gradient, V. That's not hydraulic gradient. Anyway, it's supposed to be I is 4. Given. And you're given the area. So the only real calculation you got to do is you're only given the diameter. You got a diameter of 4 centimeters, so you got to get the area. Okay, so you got to calculate. You can do that. So now you got TE equal. He doesn't define TE, the book does. He's saying time 1. It's just Q equals KIA is what you're doing. But of course there's a time element there because this Q has a certain amount of, centimeters per day. So you really don't need the TE. So anyway, you're just solving for K. There's Darcy's law. Q or IA, forget about the TE at this point. So you got 25 divided by the hydraulic gradient of 4 times the area. Boom, 497.
Is this equation for K somewhere in this reference?
Yep, but it's in the civil part.
Right.
So in other words, if you go to the civil engineering part, yeah, and also if you go to the groundwater part, which I put this is in the civil part too. But again, it's in the hydrology and water resources section. And this has all the well equations that you're going to need for the groundwater. And here's Darcy's law again. So you got Darcy's law again. So if you forgot about Darcy's law, Q equals KIA. It's there. Yeah, they don't expect you to memorize formulas. They want you to understand. They give you everything, basically. That's the idea. But they have to on a multiple choice test. Okay. So that was 91. So we go to We go to 92. Which equation would you use to calculate the flow rate of water drawn from a well? So there's Bernoulli's equation, the Depley, Hazen-Williams, rational. I think right away you could eliminate rational and Hazen-Williams, right? No? If you've taken groundwater, you should sure as hell know about the Depley. That comes up again and again and again and again, okay? Now you could say, if you overthought this or you didn't know about it, you could say, gee, well, the Bernoulli equation, that has to do with heads and everything, right? And really, the basis of the Depley formula is the Bernoulli equation, because the Bernoulli equation is the basic equation. But the point is, if I'm doing well stuff, I'm not going to start with the Bernoulli equation, okay? And so the formula that you're using is the Depley formula. So you kind of just got to know that. Like, oh yeah, I took groundwater. I've heard a lot about Depley. I hope. I hope you have. Okay, so he doesn't even mess with it. He just says, that's it, it's the Depley. That's the answer. Okay, next one. I got a saturated sandy soil. I got a porosity of 40%. Specific gravity of the sand is 2.65, and the specific weight of the saturated soil. So this is the phase diagram stuff. Okay, that's this kind of stuff that you deal with in the handout. Okay, definitions of porosity and everything, and you have to, and all the stuff is here. It's all given to you. And again, this is the kind of problem more soil mechanics. This would be more like this could be a civil problem just as well as environmental, and probably will be. So anyway, what's the answer? I got the porosity, 0.4, and it says assume you got a volume of 1 cubic foot, because what you're doing is here, I have this phase diagram, and I have my soil, I have my water, and I could have air. Now in this one, they already said it's saturated. So if it's saturated, there's no air. Okay, so really the picture you're looking at is just water and soil. And so they're telling you what the porosity is. And what's porosity? It has to do with this part here versus the whole thing. They give you 40%. And then you want to know what, you're taking the whole volume is equal to 1, so therefore the volume of the voids is 0.6. So in other words, volume here is 0.6, because you're assuming this whole thing is 1. You don't have to, but that's the easiest way to do it. And then it says, okay, if I got, now I got to get the unit weight. So what do I have to do? I have to find out how much the water weighs, how much the soil weighs. That's all I'm doing. So how much does the water weigh? 0.4 cubic feet of water. 0.4 times the magic number, which I've hit people over the head with 2x4s. I think they should remember that water weighs 62.4 pounds per cubic foot, okay? And I'm sure Victoria Bennett did the same thing. Okay, in soils. And so therefore, it's 4/10, okay? And then the rest is 0.6. So the soil is now 0.6, and you get, well, how much does 0.6 of a cubic foot of soil weigh? Okay, cuts out after a while. Yeah, automation. Save electricity. All right, so then it's 0.6. This is a little tricky because the water is, okay, 0.4 of 62.4, but this now weighs 2.65 times more than water. So it's 0.6 times 2.65. So therefore it's the 0.4 times 62.4, 0.625, 62.4, 124. Okay, kind of a simple problem because he says it was saturated, so that's pretty easy. All right. 94. Yay, a real groundwater problem. Okay. Now, when you look, I don't know if you've taken groundwater, you know what I'm talking about. If you haven't taken groundwater, you have to look at that page 171, which is the water resources part, the one here, and this is the only place where you see stuff about wells. And so here it has water resources and stuff like hydrology, precipitation, et cetera, which but we're playing with this stuff. This is the groundwater stuff. And the Depley formula is here. This is a Depley formula, but they give it to you. This is the Depley formula, and they give it to you below here. And the Depley formula for an unconfined aquifer is a little bit different than the Depley formula for a confined aquifer, but they're giving both of them to you. But the point of this is, if you haven't taken groundwater, this is steady state. I'm pumping the water, and finally, after a while, it's not coming down anymore. It's steady state. So the picture looks just like this. And at that point, you can analyze it and use the Depley formula. That's the simplest cases. The non-steady state, non-equilibrium, and if you remember, if you're taking groundwater, we're talking about Darcy and Jacob. Those are complicated problems. They're not going to give you those kind of problems. You can't possibly give you those kind of problems. No more than they can ask you to draw a flow net. Okay? They have to. So that's the idea. So the only thing you're going to have in the groundwater problems are this. Simple stuff. Steady state.
So for steady state, is something about it being level?
No. It just means the cone of depression is steady state.
Okay.
That's steady state. Because when you start pumping a well, the water's going down. But as it goes down, it's taking in more area, and finally at some point it's going to stop. After a while, it's getting enough water, it'll be essentially steady state. That's really not true in actuality, but instead of dropping a foot an hour, it's maybe dropping a millimeter an hour. After a while, that's steady state.
Okay.
Close enough. The picture looks like this. If it was non-steady state, it would be changing. And that's really harder to analyze. And they're not going to ask you that. They can't. They could ask you a general question, but I haven't seen any like that. Well, anyway, so here we are, and you say, gee, that looks like the picture we just looked at. Okay, it is. And so they're saying, okay, I got a fully penetrating groundwater extraction well. is used to capture a contaminant plume, which you don't really care, and it's an unconfined aquifer, have to know that. And you got the formula there for the unconfined aquifer, okay? And it has a hydraulic conductivity of 5 times 10 to the minus 5 feet per second during steady pumping, okay? The cone of depression is formed as shown, and the diameter of the well is, and you've got to solve. So here's the Depley equation, which you're given. And so there's the equation that shows up in this handout, okay? Depley's formula, the top one there for unconfined. And so there it is there. And that, you got that from, if you don't remember that, you got it from the page 171. And what you got to do is solve for one of the R's, because if you look at this picture, how this works, you need a certain head at a certain R. If you have an R1 and an R2, that means 2 points away from in this case, one of the R's is the well. Okay, that would actually, in actuality, that's a stupid way to compute the diameter well. In fact, you'll get a crazy answer. But that's beside the point. Let's not get detailed. The point is, I got 2 R's and I got the appropriate H. All you're doing is defining the curve, really, and it's a logarithmic curve. So therefore, this is a kind of a pain problem, but the point is you're solving. You got to solve for R1. And they give you the dimension, because if you look at the picture, if you look at the picture here, they're giving you here, it says it's 10 feet. So at the R1, it's 10 feet. And at the R2, here it's 20 feet. Okay? It's 20 feet, 30 feet away. So you got a R1, R2, and you got an H1 and H2. And that's all you do. So plug in those appropriate numbers. And the problem here, however, since this is a logarithm, you're going to have to use an exponential. So it's kind of pain in the butt, but I mean, it's no big deal. So therefore, you plug everything in. I know what the R2 is. I'm solving for R1. I've never seen a problem like this in reality. You get stupid answers. If they asked me what was the head at R1, like 5 feet away from the well, that would make sense. But anyway, that's beside the point. The mathematics is going to be the same. So you just plug in the appropriate numbers, and the only hard part is because it's just the logarithm. So whatever. I probably couldn't do it. I'd flunk. This is one where I say, I don't remember that. I'm going to guess. Okay. And so there you solve for R1, 0.27 feet, and therefore the diameter is twice that. Okay. And were they tricky here? Sometimes they're tricky. No, this one's pretty easy. The answer was 6.5, and there's no others that are close. So the math here is maybe take you a little while, that's all.
You're doing 0.27 So if you did it too quickly, you solve for the radius and say the answer is A.
Oh yes, you're right. You're absolutely right. That's the trick, yeah. Yep. Yeah, you say, oh yeah, 2.7, and you're not thinking. And that's easy to do, because you're under stress. Right. You're moving fast. So you got to watch for these tricky little, but yeah, I didn't even notice that myself. Good point. Okay, 95. I got it now. An unconfined aquifer has a soil coefficient of permeability, 1.5 times minus 3 feet per second. Now, normally we talk about it, so now it's feet per second, not centimeters per second. Initial water surface height 35 above the bottom of the aquifer. 1 foot diameter water production well. 10.5 feet of drawdown is at a flow rate of 250. The drawdown 40 feet from the well is most nearly. Same equation. Same equation. The Depley equation for unconfined aquifer. This is actually an easier problem now, because you are going to plug in okay. It's a little smaller here, but you have it. Anyway, so there you are. Same equation used before. So you plug it. You're given one radius, and another radius, and the appropriate h's. And so in this case here, this is pretty simple. You're just plugging everything in, and away you go, and solve for H2 in this case. No big deal. Okay, it's a half, but it's not a big deal. It's easier than the other problem. And so you get the drawdown. He wants to know, what they asked is, what is the drawdown?
Yeah.
And drawdown is different than, here's my aquifer, okay? And it's an unconfined aquifer, so it goes this way, okay? But this part in the equation, this is the H part. This is H here, but this part here is drawdown. In other words, that's what you're really measuring, okay? And so most places it's a small letter S, but I don't know if that's the case here. But anyway, so that's what you want. So you got to be a little careful. So in other words, they solved for H2. H1 is 35 feet. That was given. Then you got H2 is 33.4. So the difference in the 35, 33.4 is 1.6. Okay, that's the idea. So again, that's a little tricky because you got to know the difference between drawdown and the H in the formula. Because there's no drawdown in the formula actually.
Yeah.
Okay. 96. We got 2 monitor wells constructed in an unconfined aquifer. We're still unconfined. The wells are separated by 250 feet. Water surfaces upgraded and downgraded are 101 and 100.85. Aquifer hydraulic conductivity is 5 feet per day. And it says the fluid velocity in the aquifer. This is a Darcy's law problem. This is not a Depley. This is not a well. This just says I have one point here and I have another point here. Okay, I got some surface here, but the water's doing such and such. I need to know the distance here, given the 250, okay? And I have to know the differences here to get my hydraulic gradient. I have to know the difference in head versus over the 250, okay? And then I'm given the permeability, so it's just Q equals KIA problem again. And so you see here, there it is, Darcy's equation. Q equals dH dx is the hydraulic gradient, the change in head over the x distance. So, and what's the velocity? The velocity is going to be Q over A. And a given K is 5, and he solves for, well, the 101 over that's the difference in head, the 0.15. So it's a 0.15 over 250. There's a 0.15 over 250. 5 feet per day, and he gets 0.003 feet per day. Now, this is a little bit tricky because this V is not a true velocity in the soil. This is an approach velocity or a discharge, and they don't actually explain that here. They just say the fluid velocity, feet per day in the aquifer is most nearly, and of course you solve it here, and they say, okay, they get 0.003, and the answer is B. Well, that's correct, but it's really not correct, because the actual velocity is a seepage velocity, and the seepage velocity is going to be the whatever you have, the velocity we just solved for, divided by porosity. Okay? And so actually, but you go through the problem and you solve it, you get 0.003, they're not giving you any information about porosity. So by that, you're going to have to say, well, guys, you screwed this up, but I guess it's 0.003 is what I got to go with.
Is it because they asked for the fluid velocity instead of the seepage velocity?
Well, that is a fluid velocity.
Okay.
Yeah. They're not right. They should have, if they wanted seepage velocity, they should have given you porosity, because what this is if I have a permeameter, okay, and I have a difference in head, and I have soil here. The water is going through the soil. Now, what we just solved for is the water that would be going in the water by itself, because we divide it by the full area. But in other words, it's this, what they call approach velocity discharge, it'll be the same number. But that's not what happens in the soil, because the soil, there's less area of flow. Now, how do you get the less area of flow? By porosity. In other words, here's my phase diagram, okay, and if I have, this is open porosity, like we did 0.4, So that I had to divide by 0.4 because this is all the soil. I don't have the full open air. So it's kind of they should have been more careful. Well, they should have said what's the approach velocity but anyway, since they didn't give you porosity, you should have enough sense. The only number you can compute is a 0.003. And what are you going to do? Assume a porosity? You can't do that. So that's the key. And if you took a porosity number and divided it by a number like 0.5, that'd only go up to a factor of 2. There's nothing close. So, although the 0.006, somebody might guess and say, I don't know. Anyway, that's they should have said it. Let's not quibble. And then we go to 97. And it says I got a piezometer located in an unconfined aquifer and monitor on a monthly basis. The response time associated with rainfall precipitation in an unconfined aquifer in general is considered to be, and what they're saying is how much this thing going to respond, go up after it rains compared to confined aquifer. So is it larger, same, shorter? Cannot be determined without installing an additional piezometer. I don't know if the answer is obvious. If you took groundwater, yes, I think it would be. Oh, here we go. 12 minutes? The magic 20? Okay. Anyway, the confined, well, what do they say? Well, they don't say much. They just say recharge associated with an unconfined aquifer would generally have a shorter response time. So the answer is C. Now, why is that? If I have the unconfined aquifer, okay, so I get this water table here, and then I have a surface here, and it's raining, okay, you would expect this rain to get down to this groundwater faster and respond. If I have a confined aquifer way down here, okay, and now I have a rainfall, remember this is sealed here, and now I have rain, it's going to take the rain a long time to get here. In fact, it may never, who knows, so therefore no question. Again, it's what? I guess if you took groundwater, it's obvious. If you didn't, guess. I could see if you didn't take groundwater, you might guess for D. You say, well, this could be complicated. I'm going to say cannot be determined. That's not true. Okay.
So,
yeah. The picture here. It just, if I envision I have a water table a foot below the surface and it's starting to rain, you think it's going to affect that water table pretty fast, right?
Yeah.
So that's the idea.
Okay.
Yeah. Okay, here's one. It's not really a well pump problem. It's it's transmissivity. You got to know what transmissivity is. That's big T, transmissivity. It's a 45 meter thick confined aquifer. Gives you the transmissivity to 1.6 times 10 to minus 2, now in meters, okay, meter per second. 2 groundwater monitor wells placed 15 meters apart. So there we are, well number 1, well number 2. This is kind of similar to the other problem. This is really like a Darcy's problem, except what they've done, they've screwed it up a little, put transmissivity in. But anyway, it wants to know what the discharge through 15 meters here, so this part here. So I got to figure out what the flow is, and I'm going to have, of course, multiply by 50, not by 15, by 15 by 45, okay? And that's the tricky part. Well, that's not tricky, but it could screw you up. So,
is that because the confined level is 45 meters deep?
yes, it means I have a confined aquifer, and this is going to be 45 meters, okay? And then I got some surface up here, and I got 2 wells in the direction of flow, and so I got a well here in the aquifer, I got another well here, they're 50 meters apart, and obviously I got to have a difference in head, I got to know, and the difference in hydraulic head is 37 centimeters. So in other words, this difference in head between here and here is 37 centimeters, okay? So right off the bat, you say, oh, I got to worry about centimeters and meters, okay?
Would that be down at the next level?
No, this is the head in from the aquifer. This is a confined aquifer,
Right.
like a pipe.
So the 45 there, that's all confinement.
This is confined. And I got a difference here, and I got it here. So again, Darcy's law. I got a difference in head, I got to know what the hydraulic gradient is. And that's what you're doing here. But the tricky part here is this T, this transmissivity. If you took groundwater, what is transmissivity? It's K times B. It's the permeability times the B, and the B is the thickness of the aquifer. Per foot width of thing. So in other words, if I look at it, if I'm looking at the aquifer here, I'm looking at the aquifer. If I take one little part, 1 meter square or 1 foot square, that's going to give me the K. But if I multiply by B, then I get the whole K times B, which is equal to T, and that tells me how much water I can get from this aquifer per whatever unit width, in this case meter. And so if it's a mile wide, I got to multiply by, by the mile. So I need the T. So, and so you're given the T, and you're given the B, and therefore I can solve for K. And now I got the K value, and I want to get, it's a velocity term. So therefore I got the 1.6 times 10 to the minus 2. I got to divide by the 45 meters, and I'm going to get 356 times 10 to the minus 4 meters per second. So we're playing with meters. Normally it would be centimeters per second. Okay, that would be 10 to the minus 2. Pretty permeable stuff, but that doesn't matter. So now you just got Darcy's law. Now it's just Darcy's law. Q equals KIA. dH dx is I, hydraulic gradient. So therefore you just solve for your K. You know what now the area. What's the area? They asked you for a 15 meter stretch, but it's 15 meters times 45. Okay, it's this aquifer here. I got 45 feet here, and they're asking how much water am I going to get from a 15 meter part. So it's 45 times 50. And that's what they've done here. So they said, okay, it's 50 meters apart. That's my dx. How much? It's 0.37 meters because they said 37 centimeters. Okay, so 0.37 meters. And so you just putting the numbers in here. There's your K. There's your area. Area. That's the 15. Not 15. Yeah, 15 by 45. 675 is the area. And there's your 0.37 over 50. Boom. And again, all right, I'm getting meters per second, but they want meters per day. Because again, let's see, can they trick you? Yes, they can trick you. No, they can't trick you. The others aren't close. The others aren't close. So the 150 is okay. All right, the last one, this is remediation, groundwater remediation. There's not much in the handouts about it. So it just says volatile hydrocarbons may be removed from liquids well, let me state the problem. A soil is contaminated with a volatile low solubility solvent. Groundwater is very deep, soil is sandy. Technology most likely to be successful in cleaning up the vadose zone. We know that the vadose zone is the unsaturated part, right? And therefore they said the groundwater is deep, so we have a lot of big unsaturated part, and that's the part we're trying to clean, and it's got volatiles in it. Okay? So how are we going to get these volatiles out of this part? Not below the groundwater. We're trying to get it from the vadose zone. And so you look, what's the end? Soil washing? Why the hell would I use soil washing? I'm going to take all this with a volatile? I mean, I'm going to take this soil out and wash it? That's ridiculous. Soil vapor extraction? That sounds kind of reasonable, huh? That's what I'm trying to do, right? I'm trying to get the vapor out, and there are methodologies for soil vapor extraction. Land farming? I don't know what the hell you want. wetland farming, and pump and treat with air stripping. If you didn't know anything, you might select pump and treat with air stripping, except pump and treat, again, that's for groundwater. You pump it out there, you can't pump the vadose zone. Nothing's gonna come out, essentially. So if you know a little about it, it's gotta be soil vapor extraction.
So how do you know it's a vapor? The volatile?
It said contaminated with a volatile, low solubility solvent. So it's not very soluble. It's not mixing in with what little groundwater there is in the vadose zone. Because the vadose zone isn't dry; it still has water, but it's partially saturated. So it's low soluble. So that indicates it's not going to dissolve in the water very much. And they're saying volatile. So that's the key. In fact, the key is when you see volatile. And a deep groundwater. So you know darn right you're not going to do soil washing, and you're not going to do pump and treat. Pump and treat would be if the groundwater was contaminated. You pump it out, you have a treatment plant, you treat it, and then you necessarily put it back. Those are all common methods. And then remediation of groundwater that has been contaminated with hydrocarbons is commonly achieved. And again, I guess you just have to know the answer on it. I don't know, you know. So you look at this one, what is the answer?
You want to just give like a brief summary of what each of these things are for number 100?
Oh, air stripping? Air stripping is basically you're pumping the stuff out, and there's different ways to do it, but you're just kind of trying to get the contaminants from it. Activated sludge, that's like a sewage treatment process. You don't have any sludge, so what are you going to do? It's not going to be that. Alkaline chlorination, I don't know what the hell it is. Maybe help the environmental people do. And they say, that's it. Microfiltration, you're not going to go. So it has to be air stripping. Okay. You're trying to strip it from. And that's what they say. Question: volatile hydrocarbons may be removed from liquids, for example, groundwater, by air stripping. Well, okay. Now, what my intent was, we went through the problems. And I've given the stuff here. This is from the NCES book. So all this stuff here was the civil soil stuff, and that one page on the groundwater. And what I've done here with this other package of thick stuff, that's a lot of stuff we did already. The problems, okay. But then, so that's this part here, all these pages here. But then my intent was this is chapter 13 in that review book. And this is the soils and groundwater part. And I thought I'd go through that fast, just to kind of, again, and there are some problems in here too. That was my intent. Was at 5 o'clock. So we only went an hour. So that was, now this is not official now, you know, this is a review book. So it doesn't, what they say here doesn't necessarily, you know, confine the people making up the exam. In fact, they screwed up a few places, I'll show you.
Oh, if you would actually go over those areas, that would be good.
Yeah, okay. All right, so anyway, and again, soils and groundwater, you've got to go back to the civil engineering part and see what they give you, okay? Because there's a lot more here. They're trying to teach you a lot more stuff here, but that doesn't mean because it's here, you're going to see it on the exam. It's going to be governed by what you see in the handout book.
Yeah, this is very comprehensive.
Yes, this is more comprehensive. This is like, you know, I'm not teaching the way you should teach. I'm teaching you to the exam.
Yes.
Going through the problems and, okay, that's not how you teach. This is more like, oh, this isn't bad. If I go through this, I know pretty much about groundwater. So it's,
Maybe the final.
yeah, that's right. That's right. But, so that's what I was going to do. Could hit some things that.
The important stuff for the exam.
Yeah, and I'll point out the not going to ask you. Such and such. You'll see what they're not going to ask you.
Okay.
Just kind of second doing the same idea, showing you what they can ask you and what they can't ask you. So anyway, okay. Soil, you have to know a little about soil classification, and that's what's here. Now, there's different ways to classify soil. If you took intro to geo, you went through soil classification. In groundwater, we did a little. It's in the groundwater book. We didn't spend a lot of time on it. This one is one that's used a lot of times for environmental. I don't think they're not going to ask you anything about this in the exam. This is a triangular one, but what they're really going to ask you would be the civil, where is it? Well, let's just follow the book. Okay, the next thing is, if you talk about soil classification, there are terms. I don't know if they're going to ask. Actually, one year I did see this. They did ask this in the groundwater stuff. This has to do with the grain size distribution. You know, when you do a sieve analysis, you got the grain sizes, the sizes, and there are some definitions trying to characterize this curve without having the curve. And one of them is called a uniformity coefficient. Okay. Okay. And that's okay. Glad you're here. Okay. So what is the uniformity coefficient? And that has, when you see a D60, that means a 60% finer, okay, or 60% passing, if you like. And you need a D10. Now, normally what you have is there's like three numbers that you worry about. A D10, a D30, and a D60. And that some people have a D50, but I don't think on the exam they're going to ask about a D50 because it's not here. And so it's just this uniformity coefficient says, what is the size 60 versus the size 10? And if this curve is very wide, you can have a high number, big difference. And if the curve is very steep, it's a very uniform soil. That's the idea. So that's good to characterize soil. Also, there's a coefficient of gradation, and that's another way to try to characterize the soil. And when you classify the soil, you need it. And this one is where you need the D30. And it's D30 squared. And then it's a 60 times 10. And when you classify the soils, you have to actually see it fits. You need those numbers. And then specific gravity, typically around 265 for all soil. I mean, there's no use worried about it much more than that. And I don't think you're going to really need it for the exam if they tell you they're going to give you the specific gravity. They did. We did a problem. They said assume it was 265. So, but anyway, here's typical values. And we did some problems like this. Now, this is this kind of stuff. This stuff here. This is really same diagram, except they're squeezing it in. And you got to know the different air, water, soil, and the different definitions. And it's all here. Porosity, same stuff. Porosity, et cetera, et cetera. And that's where they ask you things. You know, if it's a saturated soil, it weighs so much. You know, how much is, you know, different kind of stuff. And they give you some formulas which you don't have to memorize. They would give them to you. Did they do a problem? They did a problem. Okay. So this is example 13.1. I don't know how well you can see it, but you have it there. And it says, I got a soil has a volume of 0.3 cubic feet, and it weighs 36 pounds. And they give you the G sub S. There is the specific gravity, 263, I think it is. Yeah, the moisture content is 18%. Determine moist unit weight, dry unit weight, void ratio, porosity, degree of... don't really see them giving a problem this extensive in groundwater. They will give you a problem like this in the civil exam, no question. And so anyway, you just have to, I'm not going to spend a lot of time. You just have to go through it, and it was very similar to that one problem we did already. And so you know, okay, I got, how much does it weigh? Well, it says it weighs 36, and it's 0.3 cubic foot. I want to get it into a cubic foot, so 36 divided by the 0.3, 120. Then I want to know, what is the dry density? I'm going to get this part here, the dry density. And so he goes through, W over V, I wouldn't even do that, it doesn't matter, but anyway, it gets 1017. So there's the soil part weighs 1017. He doesn't tell you here if it's saturated or not, so you don't know that at this point. So, but he tells, so now I got a dry unit weight and I got a total unit weight, so the difference is almost 19 pounds, right? Well, 18, whatever it is, 18.2. And so the question, what is that? Well, the air doesn't weigh anything, so it's water. And therefore, it weighs water, and so therefore, well, anyway. Then he's calculating, so the trickiest part, well, he's asking a whole pile of stuff, so you have to go through all this. I'm not gonna, you can follow it. It's easy math, basically. I mean, there's not much math. But anyway, you end up with a degree of saturation of 75%, which means that 75% of the voids are full of water, but not 100%. And the trickiest part that people have trouble with is, what is, for instance, when it gives it to you in English units, the trickiest part is, I've got to go from volume over to weight. And when they say to me, okay, I have 0.5 of a cubic foot of a material that weighs 2.65. Specific gravity is 2.65. And that's where a lot of people get screwed up. So you got to say, okay, that means it weighs 2.65 times more than water. So it's 2.65 times 62.4 times whatever the volume was. Whereas water is easy. If I got half a cubic foot of water, what does half a cubic foot of water weigh? Half of 62.4, okay? Because the specific gravity is 1. Right? So that follows up a lot of students. This would more or less be for civils, I think. But still, you got to know some of this. You got to know this kind of stuff. We did a couple problems like that in the groundwater part. Relative density, that's for civils. I don't think they're not going to ask you about relative density, because that has to do with strength. And then when you take groundwater, you're not going to worry about shear strength and stuff like that. Again, he's giving you typical values. That's not going to do you much good, etc. You don't really need it. I mean, if you want to go through this, that's fine. The more you know, the better off you are. And so he does have an example with relative density. Gets 61%. But for the groundwater, I wouldn't worry about it. I'm not going to ask you that. Consistency of soils. Not going to worry about that too much. Now he's at the groundwater, okay, this part. And so he's going to aquifers, confined, unconfined. We've talked about some of that. There's a nice picture. There's a picture of a confined aquifer. Same thing here. There's a, right here we have a confined aquifer. That's like the figure, right? The water level is higher than the aquifer itself. In a confined aquifer, the water level that's the level. Okay. And that's in our exam. The only thing, like when they're pumping, well, we get to the test, the P, that's always in the steady state. He's giving you some typical values of permeability. Again, they're going to give you the permeability if they give you a problem. They're not going to ask you like, oh, assume the permeability and then go. They can't do that, not on a multiple choice test. So they're going to give you the permeability. They always have. And so he's just going over Darcy's law. Q equals KIA. Just showing you this here. I hope whether you're environmental or civil, you should be able to do that. Okay. And he does. He says a sandy soil has a coefficient permeability of such and such centimeters per second at a void ratio of 0.5. Estimate K at a void ratio of 0.7. How am I going to do that problem? How do I know this K1, K2 divide? Well, because right above here he gave you these formulas. I haven't seen those on the handouts here. I don't think they're going to ask you that kind of question, because I haven't seen any relation like that and these are empirical anyway. They're not actually, so I doubt if they're going to ask in the groundwater part. They might ask the civils. Here we are, flow nets. And this was the flow net part. There they are describing the flow net here. And so how do you use the flow net? Yeah, and if you still get into groundwater, we made you draw some flow nets. That's not so easy. It's a trial and error solution, so there's no way they can ask you to draw a flow net. They're going to say, here's the flow net, do something with it. And here's the formula. They want to say, okay, here's the sheet pile, here's the flow net, how much water is going under the pile, and here's the formula. I need to know the permeability, I need to know NFND from the flow net, and I got to know the difference in head. So the difference in head is easy. NFND means the flow tubes versus the number of drops. So in this case, you got 1, 2, 3, 4 flow tubes, that's the NF, and each one of these is an equal potential with a head drop, so I got 1, 2, 3, 4, 5, 6. So the NF over ND is 4 over 6 in this case, by the head, and the difference here is that H. And that's really all this is here in the handout. They've given you a similar flow net, and they've told you the formula. I mean, if you go down here, Q, you see Q equals KH NF ND. Same thing, so it's here. So if you say, gee, I don't remember the formula, well, there it is. Except you got to know what an FND is. So now in this case, we have 1, 2, 3, okay? And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it'd be, okay, so that's what you got there. And he does a problem. So he says, refer to the flow net shown in figure 1311. Given K is such and such, H, he gives you H is 30, and then he gives you H2 is, in other words, H on one side is 30, so the difference is 25. And so that's a pretty simple problem. You just plug in the K, gives you the K. So you got to play with units because he wants it. So he gives you the K. You got the 4 over 6, the NFND, but you got to get, since the permeability is in feet per minute, what do they want to do? Refer to flow net per day. Okay, so you got to do some unit conversions. That's all. And the 4 over 6 and the 30 minus 5 is where you go. They might ask you, they've asked the civils, I haven't seen it in the groundwater exams, they might ask you about heads, about pressure heads, because you get that from the flow net, but I'm not going to, like they've had a picture of a dam, and then they've said, well, what, if I put a piezometer in here, what would be the pressure head coming up through here? And
they give you the cube flow, and then solve the head.
If they give you the flow net and they tell you what the H's are, and they tell you the permeability, they don't have to tell you what the Q is, because you can compute the Q from that info, and then once you have that from the flow net, you can actually calculate a pressure head. So you're talking about an elevation head plus a pressure head equals a total head. These differences here are a total head, differences in total head. So you gotta go through that. I haven't seen that. I don't think they're gonna ask that in the groundwater part. They'll ask the civils. They may ask the civils. They have asked the civils. What's the pressure head at the end of the dam? Effective stress, they are not going to ask groundwater people about effective stress. That's for civils. They mention a little in the groundwater, but I've never seen them ask anything about effective stress in the groundwater part. Because you're talking about shear strength now and stuff like that. Consolidation, they're not going to ask you anything about consolidation in the groundwater part. But they will ask the civils, maybe, about, well, they will. They will. And groundwater flow. Well, this is like one of the problems we did. I mean, the picture looks the same way. There's Darcy's law. There's the differences in head, okay? And the fact this is going up, it doesn't matter, okay? It doesn't matter if this is going, I mean, you say, wait a minute, this aquifer is going up. So what? It's like a pipe. I'm interested in the head here and the head here. I don't care what this pipe can be anyway. It doesn't make any difference. It doesn't have to be level, okay? It's the head difference in head. So I got to know the difference in head. I got to know the distance. I got to know the permeability, of course, of the aquifer. Got to know the area, and away I go. And that's all he's saying, Darcy's law. And he's done a problem that way. So there's your aquifer down here. I got the differences in head here. And what's he asking for? Find the pore velocity. Now, here he says pore velocity. So they're going to have to tell you what the porosity is. Let's see, observation wells, soil borings, some elevations. Soil has a porosity of 0.22. So given.
Is pore velocity the seepage?
Yes, seepage velocity. Yeah, that's the water going through the pores, which is not the approach velocity, like we said in that problem. So anyway, he goes through it. It's just Darcy's law, but then you notice he gets V Darcy. He's calling V Darcy. That's the big V, the approacher. So he gets 2.7 times 10 to the minus 5 feet per second, and then what's he got to do? Notice he divides by 0.22. I'm saying he. I don't know who wrote the book. He, she, they. Okay? So divide by that, and the actual pore velocity is going to be about 5 times faster. Okay. Well, and he says, okay, about 10.6. Well, that's fine. Now, well hydraulics. He says the theme solution here, the steady state theme solution, and he's going through the derivations, and what he ends up with, here's your Depley formulas. So you go to the next page, and here we are. He said, here's my unconfined aquifer, here's my confined aquifer, and here's the equation. Well, this was the same equation that's in the handout. Okay. And in the case of confined, it's very similar, but the difference in unconfined is you end up with a 2. There's a factor of 2. I'm not going to try to go through derivations. It's a simple, stupid little algebra, okay? But anyway, you end up with a 2, and you end up with also the thickness of the aquifer B, because you got to know how thick the aquifer is. I don't have to worry about that here. So there are two different formulas, but very similar, and they got logs in it. Okay, and these two are the same equations that were given, and these are steady state. So we've done some problems like that. So no use fiddling with it. But in reality, the most important part, and what most people do, is unsteady state. That's called Dyson-Cooper-Jacob, and that means I can't wait forever for this thing to get steady. So therefore, as I'm pumping, it's dropping. And I want to analyze it as it's dropping. And that gets more complicated. And I don't see them, and I never have seen them ask numerical problems about Dyson and Cooper-Jacob, because they're very complicated. And I'm not even going to cover it. If you want to browse through it, Dyson and Cooper-Jacob are doing the same thing, but anyway, Cooper-Jacob is a little simpler method after things kind of settle down. I'm not even going to mess with it, but just to show you that if you took groundwater, you did problems like this, where you actually have to have, these are two plots. One is an actual plot, a theoretical plot, that's this one, and then one is an actual plot of how it looks. And you basically have to fit one over the other, and you get points, and you solve. Well, they can't ask you to do this. They can't ask you to do this. They might ask a general question, like, well, in the Dyson solution, do you, I don't know, but I haven't seen those kind of questions. So I wouldn't worry about unsteady flow. Groundwater contamination, there's a lot of reading here. NAPLs. There is stuff about NAPLs, D NAPLs and L NAPLs in the handout, the book, okay? In the environmental part. Not in the civil part, in the environmental part. There is stuff about some NAPLs and different kind of things. This equation here is called the advection dispersion model. The solution to this, we could spend 3 hours, 4 hours going through, okay? And that's the basis of most modeling. I don't see them asking you a damn thing about this. It's too complicated. Could they ask a textual type question about it or something? I don't know, but I haven't seen it. Because I don't know what the hell they can ask you without giving you the whole equation. I just don't see them doing anything on the modeling part. Anyway, that's what you end up with. They're not going to ask you that. It's going to be all steady state. Retardation of contaminants. This was the one we talked about, factor of 5, that the contaminant's going to move 5 times slower, or the groundwater is moving 5 times faster than the contaminant, if you like it. That was the retardation, and that's what that's what he's showing you here. Retardation factor. He's going through it, but it was actually given in the It's just the velocity divided by the retardation number. This one he's going through the, I don't see it going through the mechanics of this. They'll just say the retardation was blah, or something similar. And I would recommend that you do. We did do some problems, and I haven't seen any numerical problems on remediation. They've always been the kind we saw. How do you get rid of the volatiles? Air stripping, blah 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 blah, and you take a choice. Same thing with how do you get rid of the hydrocarbons? Air stripping, pump and treat, blah blah blah. So you gotta have it, but they've all been kind of, you either know it or kind of don't know it. But I would say it would be worth reading this part, because I'm sure you're gonna see a couple, and this just bears out a lot of stuff we talked about. In-situ treatment is looking out here how to do it. Then it does talk about pump and treat. Other than that, it doesn't really go over too much. And then we get some more problems. And again, this is not the official book, this is from this book. And you can get a lot of different kind of books and a lot of different kind of problems. So anyway, we got a whole bunch of problems which we probably should go through. Got 11 problems. And they are pertinent. So this one says, I got a moist soil specimen. I give you the volume, and it weighs so much, kilonewtons. Water content's 12%. Specific gravity is 269, given. You don't have to know. And again, it wants all this. Moist unit weight, dry unit weight, vibration. Civil. This is a civil problem, really. And so if you look at 13.1, we kind of covered it the same way. You find out how much it weighs. You got to be the units, kilonewtons per meter cubed. Say what's the density of in SI units? What you usually express unit weight in kilonewtons per meter cubed. Because you say what's a cubic meter of water weight? 1,000. So if I had 265, I say I got a material that has a specific gravity of 265. What is it in kilograms per meter cubed? It'll be 2,600. Okay, but you don't need that here. But anyway, he's give you the numbers, and you're fiddling around, finally come up to degree of sag. We've kind of gone over that stuff, but you might want to play around and understand that a little. They probably wouldn't ask you all this. They're going to go through something, and they're going to ask you one thing. When you go through, they'll say, what's the weight ratio? All the problems, they can't ask you. Well, they can. That would be 4 problems. Okay, so you may want to spend a little time. So it says I got a soil deposit in the field. I got a dry unit weight, kilonewtons per meter cubed. From the laboratory, the following were determined, given again in G, and it gives me a maximum and a minimum void ratio. Find the relative density in the field. That's a civil problem. 13.2. They're not going to ask you that in the groundwater part. Civils, yeah, they'll ask you that. They could. This one, I got a sandy soil. I've given you maximum minimum void ratio. Relative density, again, they're not going to. They're asking unit weight, but it's relative density. They're not going to ask 13.3 either. You may want to look it over. But 13.4. This is a flow net. Refer to the flow net shown in figure 1.4. Well, I can never find figure 1.4. I don't know if it was in figure 1.4 early in the book or what, but I didn't have it. But anyway, it says they give you the K, they give you the H1 and H2, so you know the difference in head. Determine the seepage loss per day. Well, I got to have the flow net. And when they solved the problem, here, they got 4/6. Okay, so I think it was like the one we looked at when we were going through the review. It was under the sheet pile. Yeah. 554. I had it marked someplace, yeah. Right. I think that's it.
Probably something at least similar to that.
It's, yeah, because I need the 4/6. It does. It could be under a dam, but it's got to be the 4/6. There's different ways to come up with 4 over 6. So in this one, yeah, you could say it's that one. And you got 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Okay, and all the rest you have. And so therefore you just plug away and away you go. You got the answer. Okay, that's a pretty simple problem. I guess the only thing you'd screw up is the 10 minus 1.8. You got to understand the difference in head. So it's 10 on one side, 1.8 on the other side. In other words, there's a tailwater. It's 13.5. Results of sieve analysis. Okay, he's giving you the results of the sieve analysis and asking what is the coefficient of uniformity coefficient and coefficient of gradation. Well, they're not going to ask you that in the exam. They can ask you one of them. They can't ask you two of them. Okay, but anyway, it's better to know how to. So what do I need to know? I need to know a 10, a 60, and a 30. And guess what? Actually, they screwed up. This is wrong. There's no 30 here. Okay? And if you look to the problem here, this is different than this one. So in other words, with the problem, 13.5, this is not right. That's not the right one. And what they've given you here in the solution is the right one.
Okay.
Okay? So therefore I need to know the 60, the 10, and the 30. So that's it. So we just plug in D60, D10. That's it. Plug in the numbers, there you go. 13.6 is a consolidation problem. They are not going to ask you that. Not in the groundwater part. Normally consolidated clay, the groundwater people don't necessarily have to even know that. If you took into the soils, you should know it, right? Are you environmental or are you civil? Then you can solve a consolidation problem. You'll probably they will have some simple ones. But I'm not going to cover that tonight. Okay. I assume Victoria probably covered.
Yes.
Yeah. Okay. She's in Minneapolis. Okay, a 13.7 odometer test. It's not going to ask you that. That's consolidation again. Civils, yeah. You could ask you that. And that's fairly simple. All you need is difference in void ratios. P1 and P2, away you go. And the compression index is the slope of the curve. And that. 13.8, a soil core, 5 meters, 10 centimeters, weighs so much, porosity is so much. Again, this is a phase diagram. Estimate the degree of saturation. So on 13.8, we've already done some problems like that. They could give you that. This could be for groundwater too. This could be for groundwater. You got to get the volume of the cylinder, so you got to calculate the cylinder. I got to know how much the solids weigh, how much the water weighs. And I got to know, what the appropriate volumes are. So first, you work from the right side with the weights. In this type here, you work with the weights, and then you have to get over to the weight side, or vice versa, whatever, depending on what they give you. And then when you get all that finished, you're done. So, how the weight of water? Well, he knows how much 22 grams, 1 gram per cubic centimeter. I can get the weight of water. And I got to get the weight of solids. That again, it's a little tricky because you got the 265 part in there. But you'll notice in this case here now, he's using 1,000 kilograms per meter cubed. And he gets so much kilograms and so much grams. So he knows how much the volume of the solids are. He knows what the weight of water is. He can get the volume of the water just divided, in this case, just by 1, because it's 1 gram per centimeter cubed. And then finally, degree of saturation is how much you got to get the volume of the pores down. If it is in soil, it's pores. And how much of the pores are filled with water. That's the degree of saturation. And if you took intro to geo, you did a lot of problems like this. Okay, so you may want to review. 13.9. Estimate the soil phase concentration of Tuli in a contaminated aquifer. I don't even know how to do this. This is an environmental problem. Okay. So if I was taking this test, I would guess. I don't know what the answer was. Let's see what he got. Aquifer, affordability. is 490 and the organic fraction is 3.5, you may assume the relation is such and such. I wouldn't have time to go screwing around there looking for it, okay? So if I run into this kind of problem, if I was taking this test, I'd just guess. What am I going to guess at? I'm going to say 548. 13.9. Wrong. 422.8. Or 423. Why did I say C? I'm a pilot, and they give multiple choice tests, and you have to take exams for different kind of things, private pilot flight, instrument rating, different kind of stuff, and it's very, problem like this. And it turns out, most people say that if you don't know what you're doing, guess the third one. And the odds seemed to, I don't know if it's true or not, but whenever it came out, we'd guess the third one. It turned out, seemed like it worked. Don't think that, don't go by that. Yeah. But anyway, I don't know how to do that problem. So we better ask the environmental person. I hope Kilduff covered it. All right. So now here's a groundwater problem. Water's pumped 1310. Groundwater's pumped, rate of 250 GPM from an unconfined aquifer, 75 feet deep. Wells are located 150 feet. Drawdowns are 9 and 7. Find the hydraulic conductivity. Okay. And what are you going to use here? They don't say, they just says 250 GPM unconfined aquifer, 75 deep, determine hydraulic conductivity. They don't tell you. I mean, they would have to tell you steady state or something, but this is the book. So the book, maybe the book, it's just the book. It doesn't have it. Okay, we go again. Okay. Okay, so 1310, guess what? Right there. There's Depley's formula again for a steady state. Darcy's law for an unconfined aquifer. That's the Depley formula. And that's the one that's for the unconfined. And that's the same one. And so now it says we got CFS, we got to calculate, get it to CFS from GPM. So you got to know how many gallons there are in 7.48 gallons per cubic foot. But it's here. It's here. If you go look through the, where you might have to search for it early in the, like, fluid mechanics or something like that, there's a bunch of conversion factors too, if you look through the book. If you look through that handout book, there's a whole bunch of conversion factors. So you want to look through that NCES book so you know where you can find stuff. Not only groundwater, not only soils. Remember, in the morning you're going to have statics, dynamics, all that kind of stuff, and same thing. You can find a lot of that stuff there. So like how much does water weigh? There's a whole pile of stuff. So you want to browse through that book to know where stuff is. So anyway, there he goes. He gets it to CFS, and so now I got to have two radiuses and I got to have two H's, and so he solves it. And so he plugs in, he's got H1, H2, there's your CFS, logarithm, the distance, away from it was 150 and 100 given, the distance is away, and then I got the pi term, and then I got to know the difference, the 68 to 66, and actually this is wrong. Because it is an unconfined, wait a minute. No, this one is okay. This one is okay. Yeah, this one's all right. Sorry, it's the next problem that's wrong. So this is correct. And what you need is the 68 minus the 66. It doesn't you don't really care what those numbers are, but you got to know the difference. Well, it does matter here because it's a square. But that's important. They screwed up on the next one. The next problem, 1311, they're saying, what if I have, where's 1311? I got the answer. Where's the question? I don't know what problem 1311 is, unless I didn't copy it or something. But 1311 is a similar thing. It's the same problem.
Mine says we work from 1310. The aquifer is defined.
Yeah. Okay, I don't know, I must have skipped a page here. Anyway, so now it's a confined aquifer. And again, there's your Depley assumption again, except they put a letter M here. I don't know why you put this letter M, this is the thickness of the aquifer. Okay, so there's the 557, same as you had before. There's your 150 and 100, same as you had before. You just plug it in. There's your 2 pi, and the M is the 75 feet. This is a confined aquifer, 75 feet thick. Okay, and then they say 68 minus 66. It turns out they got the right answer for the wrong reason. Because this is a confined aquifer, this says the confined aquifer is 75 foot thick. Okay? So I got a confined aquifer 75 foot thick. And they're saying that I have a 68 and a 66 is the head. This is H from the bottom of the aquifer. How could I have, if I'm 75 feet here, how could I have 68 feet here and 66 feet here? That's screwed up. Now, if you say from the top of the aquifer it was 68 and 60, that's okay. Now, it turns out it doesn't matter because what you need is the 2 in this case. And there's no square here. There's no square here, so it doesn't matter. Okay? So this is actually wrong. They should, but the difference is 2, and that's what's important. So the answer is correct. Whereas in the unconfined, you have to pay attention because it's a square. So you can't just say the answer is 2. But remember, in the this is the confined aquifer, so therefore we're talking about, water being up high. So if this was the 68, that'd be okay. Now in the unconfined aquifer, of course, the formula is different because now you're talking about this, okay? And therefore you say, oh, I got an H here and I got an H here, and that's what he did. That was the 68 to 66. That's okay. But that's actually wrong here. So they didn't give you enough info here. You actually, they would have to tell you what, where reference what. How could I have 68 and 66? That's less than, it wouldn't be any confined aquifer. So it's a screwed up problem here. Okay, to go out to the book. It's a typo. But it gets the right answer. Well, that was about it. That's what I was going to cover. We took, not quite 2 hours. Now, with this huge audience of 84 people here, if there were any questions, I would be asking. But since we don't have 84 people here, I guess we call it quits.
Thank you.
Okay.